Hi. So in this session, we are going to discuss another very famous interview problem, which is again famously known as trapping rainwater problem. So the very first thing we will do obviously is to understand the problem statement, and then we will go forward to discuss the brute force and then few optimized solutions. So the very first thing, as I said, let's try to understand the problem statement. So the problem statement said, given height of n buildings, find out how many units of water can be stored in between the buildings. Consider width of each building to be 1 unit. So as you can say, there is no mention of rain. So you might be wondering, why is it trapping rainwater? So there is a statement that consider it's raining. So let's say I write this. So consider it's raining, and consider you are given height of n buildings. Find out how many units of rainwater can be stored in between the buildings. Consider width of each building to be 1 unit. So here we are given an array. This array is actually the height of these buildings, and we can see here that width of each building is 1 unit. So it might not look very uniform, these blocks, but all of them are 1 unit, let's say. And these are the height. So what do you mean by 0 height? Which means there is nothing in here. The building height is 0. Then we have height of building as 1. This is 0. Then we have 0 height building. Again 0 height building. Building of height 3, 1, 0, and again 3. And now what we have to do is we have to find out that how many units of water can be stored in between the two buildings. So consider this complete arrangement. What is the total amount of water we can store? So before we go on to solve this, let's see few fundamentals. So obviously, if we have to store a water, we need two boundaries to stop the flow of water, obviously. So if this is a container, we can store water till here. But if we have something like this, we can't store water. Obviously, the water will just flow off. So for here, for the buildings to trap water, we want that at least two buildings should be stopping the flow of water, and the water will be stored in between the two, right? So starting from here, let's try to see that how many units of water are stored. So here we cannot store any water because this building is height 0 and there is nothing on the left to stop the flow of water. Same is the case here. Now we come here. Same is the case here. We cannot store any water. Now we come here. So we have two buildings of height 0. We can store water till here. After that, obviously it will flow out. Now let's try to see how many units of water is stored. So this is 1 unit of water. This is 2 units of water. This is 3 units of water. And this is 4 units. So we have 1, 2, 3, 4. 4 units of water can be stored in this particular space. Let's proceed further and see if we can store more water. So after we come here, we cannot store any water above this, it will flow off. We come here. So we can see that there is some space above this building, and also there are left and right buildings which are there to stop the flow of water. So here we can store water till here. And now let's calculate how many units of water we have stored. So this is 1 unit, right? So obviously this 1 unit is occupying the space. So we can store water only above it. So we'll have 1 unit water stored here, 1 unit stored here, and we have 3 units stored here. So total units stored in between these two buildings is 5 units. So considering the complete arrangement, the total unit of water stored is 9 units. And this is the problem statement. You are given this particular arrangement in the form of array, in the form of height of the buildings, and you have to tell us that how many units of water can be stored in here. Now we have to think, how can we find out? So one basic thing that I said is that for storing the water, there should be something in the left and there should be something in the right. Next is that, let's say we have a container like this. So the total amount of water that we can store is dependent on this particular boundary. No matter how long this boundary is, we can't store water after this particular point. Another point is, like, let's say this is a container which can hold 4 liters of water, or 4 units of water, let's say. And what we do is that we put a block, let's say a wooden block that is occupying space for 2 liters of water. So we can store only 2 liters of water. So this is a wooden block and it is occupying the space of 2 liters of water. So we can't store complete 4 liters in here. We can just store 2 liters in here. So these three things will help us in solving this particular problem. So height of any particular building, how can we find out that how much more water can be stored in and around that building? So again, I'll make this particular picture. Okay, so let's say we have 0 here, 1 here, 1 here, 0, 0. Now, as I said that here there is nothing left in, so there will be 0 water stored, 0 and 0. Now, how much water can be stored in this particular part? In this particular part depends upon that what is the maximum height of building at the left and what is the maximum height of the building at the right. Listen to me carefully. So we have to see the maximum height of building at the left and maximum height of building at the right. So let's say this is the maximum height of building at the left and at the right. And from the maximum heights also, the water will be stored as per the height of the minimum of these two maximum. So let's say this is L max and this is R max. So going by this particular concept, the water stored is going to be minimum of L max, R max. I'm talking about just this particular part. This particular part I'm not considering right now, just this particular part. Now this is the water that can be stored above this. Okay. Now let's say there is a building here of 1 unit. Okay, there's a building here of 1 unit. Now going by this particular part, the total water stored will be minimum of L max, R max minus height of that particular building. Obviously, it's going to be just 1 unit, right? And for here, since we don't have anything, the height of building is 0, it's just going to be minimum of L max, R max, which is 2, minus height is 0. So in this space, the total water stored will be 2 units. So this is how we are going to see that what is the unit of water stored around this particular building or around any particular building by this formula. So the total amount of water stored around a particular building is going to be minimum of L max, R max minus height. Now we have to think that for each and every building, how do we get to know the L max and R max and height of the building we already know. So let's first see a brute force approach for this. Now let's see how do we solve this particular problem using brute force approach. So in brute force, what we do is we try all the possibilities. So as we saw that the unit of water stored is equivalent to minimum of L max, R max minus height of this particular building. In this case, when I'm calculating L max and R max, what we have to do is we have to include the height of that building while calculating this. Because obviously if we have something like this, just see it logically, then in that case you might get L max as 2 and R max as 1. And since the height of this building is much bigger than 2 and 1, no water can be stored above this, right? So we have to ensure that while calculating L max and R max, we include this particular building. Now, let's see how we can calculate L max and R max. So what we are thinking of doing is that for each particular building, including that building, I'll run a loop from this building to the left and I'll find out what is the L max for each building. Similarly, I'll go from this particular building to the right and I'll find R max. So if we are including this particular building while calculating L max, this is what we will do for each and every building. And once we have L max and R max, for every building, we'll do this particular operation, that water is going to be minimum of L max, R max minus height. And whatever is the unit of water above every building we keep on adding that to our water variable. So let's see if we can write code for this. So what I'll do is I'll run a loop from I equal to 1, I less than n minus 1, n plus plus. I'll initialize my water with 0. My L max, I'll make it, let's say, a of 0. And R max, a of n minus 1. And we know that there couldn't be any water stored above this building and this large particular building. So we'll run a loop from this building to this particular building, from 1 to n minus 1. Now, what I have to do is for each building, for each I have to calculate L max and R max. So how do I calculate that? So I'll do for j equal to I, j greater than equal to 0, j minus minus, if r of j or a of j, let's say it's r, this is him, let's say this is r of 0 and n minus 1, r of j is greater than L max, we update our L max to r of j. Okay. Similarly, finding the right max for j equal to I, j less than n, j plus plus, if r of j is greater than r max, we update our r max to r of j. Fine. So now I have L max and R max, and after these two loop finish iterating, we will calculate the water stored. So the water stored till this particular building is going to be water stored till now plus minimum of L max comma R max minus height of this particular building, which is R of I. So this gives me the complete water stored in between these buildings. If we see the time complexity, this loop runs for n time, and for each iteration of this loop, we have these two loops running combined for n number of times. Hence, the total time complexity is going to be O of n into n, which is O of n square. So now, the time complexity is O of n square, space complexity is O of 1. So let's see if we can optimize this further. Now let's see an optimized approach for this. So before we go on to directly write the code, or before I go on to tell you what is the optimized approach, let's see a small observation. So let's say for this particular building, I'm calculating the left max and right max. And similarly, I'm doing for this and this. So what sort of optimization can we do? So when you are writing a code and you're looking for optimization, in this particular case, we can see that we are doing some sort of same operation again and again. So if we have to calculate L max for this building, I'll traverse this particular part to get L max. If I have to calculate for this building, I'll traverse again this particular part to get L max. For this building, again I'll traverse this particular part to get L max. And for this, again I'll traverse to get L max. Now, can you see that this particular part is common in all the cases? So, for this particular building, let's say for this particular building, I have already calculated L max till here, right? I have already calculated L max till here. So, for L max of this particular building, let me call this L max. And let me call this L. So for L of this particular building, there could be just two scenarios, that height of this particular building is greater than L max, or height of this particular building in less than L max. So if height of this particular building is greater than L is equivalent to height of that particular building, and if height of this building is less than L max, then simply L is equivalent to L max. Similar thing can we do for this particular place. So height of this particular building, so let's say I have my L max till here, till this particular building. Again, for this building, we have the same scenario, that we either have height of this building greater than this L max or less than this. So both the cases, we can update the L max accordingly. Similar thing we can do here, 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 and here. Similar set of operations we can do till R max. So if you are understanding, what we are doing is the calculation that we have already done before, we are trying not to do it again, rather use that calculation to get our further results. So in this case, in this particular case, I already have L max till here, I can use this L max, right? Similarly, in this particular case, I already have L max till here, I can use that. Similarly, in this particular case, I already have L max till here, I can use that. Rather than again going to this particular loop and finding L max again and again, similar can be done for R max. So what we will do is, we will store L max till a particular point. Hence, I will store R max till a particular point, and I'll use that in the further calculation. Whatever L max I get here, I store that. Whatever I get here, I store that. Here I store that, here I store, and I use that in calculation of next L max. And how can we store L max? We can store L max for each and every building using an array. Let's say I call this left array. Similarly, I can use right to store right max. Now let's try to understand this approach even further. So first, let's run our code once, just see it, whatever logic we have in our head, let's just implement that logic before writing code for it. So before we just directly jump to write the code, let's just see through this example that whatever we are thinking is right or wrong. So let's say we have left. In this, I'm storing all the L max, and then we have a right, storing all the right max. So here, obviously, left is going to be 0. Okay, this is the first one. This is going to be 0. For this particular place, again, I have two things, that this 0 is greater than height of this, or this is less than height. So if value of array of I is greater than the element that is before, which is left I minus 1, I will simply update my left I to array of I, else I'll update my left of I to left of I minus 1. So in our case, this is greater than the previous element. So what we will do is, we'll update left of I with 1. Now here again, left max till here is 1. So we'll check if left max till here is greater or lesser than this particular way. So we know it's lesser. So we update this with 2. Now here till here, now for this particular place, I'll check that whether left max till here is lesser or greater. It's greater. So we fall in this particular category. So simply update our left to left of I minus 1, which is 2. Similarly here again we'll update 2. At this particular place, L max till here is 2 and height of this building is 3. So I'll make it 3. Here again I'll make it 3. This will be 3 and this again will be 3. Similarly, we'll do it for right, and right we will move from right only. So let's say I update this to 3. At this particular place, whatever right till now is there, it is greater, so we'll just update it to the previous right. Here again, right till now is 3, which is greater than this particular element. I'll update this to 3 as well. This is 3, which is equivalent 3. Again till here, what is happening, that this value is much lesser than right till now, so I'll update this to 3. For here, I'll update this to 3. For here again, I'll update to 3. So I hope I've updated all the elements. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. So we'll have one more 3. Okay. So now for every I, so let's say we have 1, 0, 1, 2, 3, 4, 5, 6, 7, 8. So for every I have the left max and I have the right max, and I have to just use left of I, right of I, whatever is the minimum of the two, minus height of the building, gives me the amount of water that can be stored in this particular building. So the minimum of this 2 is 3 and height of the building is also 3. So this gives me 3 minus 3, 0. So in this case, minimum is 3 and height of the building is 0. So this gives me 3. In this case, minimum is 3, height of the building is 1. This gives me 2. In this case, it gives me 0. In this case, minimum is 2. Minimum is 2. Height of the building is 0. This gives me 2. Again here, it's going to give me 2. Here we have minimum as 2 and height of the building is also 2. So this gives me 0. And again, this gives me 0. So total water stored is going to be 4 plus 5. It's going to be 9 units. So this is how we can use the concept of storing left and right. So in this case, if I see the time complexity, then time complexity for making this particular is O of n, for this is O of n, and obviously we are running one more loop for computing the value. So this is going to be O of n time complexity, and we are having O of n space complexity. So this is how this particular approach works. Let's see the complete code for this. So now let's see how we can write code for this. What are the steps that we have to perform? We have to make left array that is containing all the L maxes. We have to compute right, and then we have to iterate through the array to get water amount. So what we will do is, we'll have a left array of size n, a right array of size n. We'll initialize left of 0 with array of 0. Now I'll run a loop from I equal to 1 to I less than L n, and for every I, we check that if array of I is greater than left of I minus 1, then we update our left of I to array of I, else, okay, this was here only for this, else left of I is going to be left of I minus 1. Similar thing we'll do for right. We'll run a loop for I equal to n minus 1, I greater than equal to 0, I minus minus, if error of I is greater than right of I plus 1, then we update our right of I to right becomes error of I, else it is going to be right of I equivalent to error of I plus 1. Sorry, it's right of I plus 1. So now I get my left array and the right array. Now we will write code to calculate the water amount. So I'll run a loop from I equal to 0, or I can run it from I equal to n minus 1 to n minus 1 also, less than n minus 1, I plus plus. Let's say I have a variable water which is initialized with 0. What I'll do is water plus is equivalent to min of left of I comma right of I minus error of I. And obviously we are going to either return this water or print this water. So this gives me the complete amount of water that can be stored in this particular case. So as we can see, the time complexity is O of n and space complexity is also O of n.